Hey everyone, and welcome back to the fAQ podcast season 2. So Adam, last time we decided to move away a little bit from the theory behind quantum physics. We talked for a while about qubits and superposition and all of these ideas. But in season 2, we chatted about this idea of really getting concrete and actually understanding some of the physics and engineering behind these ideas with the goal of kind of making them more solidified in our minds. Last time, you mentioned this idea, which I really like, which is to go through this well-known checklist that folks are using nowadays to build quantum computers called DiVincenzo's criteria. So this is like a list of 5 things that if you want to make a quantum computer, you say, okay, check box number 1, do I have this? Check number 2, do I have this? And then this lets you, tells you if you're on the right track or not. So I'm excited to be here with you today so that we can go through one of these criteria and make our way through. But maybe we should start off with, the actual topic of quantum computers. I don't know. What do you think?
Yeah, no, I think that's right. And yeah, excited to jump right into DiVincenzo. But yeah, let's start off with kind of laying that basic foundation so we're all on the same page. What is a quantum computer? So I'd love to get your gut reaction to that. What would you say in a sentence about what is a quantum computer, Tai-Danae?
Yeah, okay. I like how you said one sentence because here's the thing. Although all of season 2 really is about quantum computers, what does that mean? Let's pick a kind of quantum computer and talk about it. I think it would not be too helpful to start off this episode by trying to give some loosey-goosey, imagine you had this, or think about how classical computers work, blah, blah, blah. Because at the end of the day, if we don't actually understand, when you look under the hood, what's going on, I think no amount of analogies or trying to make comparisons to explain this thing is gonna help. So maybe what could be helpful is your idea. How about here's one sentence of how someone can think of what a quantum computer is, and then the entire rest of season 2 is unpacking what that means. Okay, so I just kind of want to put that up front.
Definitely, yeah, that's where we're
okay.
at. So yeah, what do you think if there's? I know how podcasts or on quantum computing or other kinds of material in quantum computing would usually start talking about bits and qubits and states and all of these sorts of things. And we don't want to do that. That's these sort of sound bites. We're going to, you said, take the entire season to go through and make it so that when you hear something like that, you can actually understand it. The ironic thing, I think, is that those sentences, there's nothing wrong with those sentences and those kind of those sound bites. But the thing is that I think you have to already be an expert in the field in order for those sound bites to actually make sense. Yeah. And so it's a little bit backwards of trying to introduce folks that might not know a lot about quantum computers. Yeah. It's tough to introduce them with this sentence that really you have to already be an expert to have it make any sense. But I think that there is still a way to sort of talk more generally about quantum computing at the top. And I think you have a great way to approach that.
Yeah. Okay. So here's the way that maybe is great or maybe is not. But here's one way that you can describe what a quantum computer is. Okay. So when folks ask what is a quantum computer, I like to answer that with, it's a computer that processes, stores, and shares information in ways that are fundamentally different than the computers we're all familiar with. Okay, so it processes, it stores, and it shares information in different ways. What are those different ways? That's what all of fAQ season 2 is about. So I know that's not super satisfactory, but I think the payoff at the end, if folks stick with us, is that then we'll kind of understand really what that means and really what folks are doing in this space.
I think that's great. And yeah, the only thing that I'll throw into that is to have in your mind when you're listening to all this is that quantum computers are not just regular computers, but faster. That is what they're not. So we're going to get much more into detail, but I think having that in your mind of we're not just talking about accelerating the computer that we're using to talk to each other. We're actually talking about a whole different way to process, store, and share information, that fundamental difference that you're talking about. Yeah. But yeah, no, I think that's great. So should we just get right into DiVincenzo's first criteria?
Let's do it. Let's dive into it. Can you tell us what the first criteria is?
Sure. So as you mentioned before, there are five, but the first criteria is a scalable physical system with well-characterized qubits. So I think maybe one way we could do this is unpack that and
Let's
go
unpack
through
it.
it.
Yeah.
And let's do it in reverse,
Love it.
maybe, because let's not bury the lead,
Yeah.
and we can actually talk about qubits, because I think we mentioned last time that we're going to focus on trapped ion qubits.
Yeah.
So maybe we can start talking about those qubits a little bit, and then kind of work backwards into what does it mean to be a well-characterized system? What does it mean to be scalable?
Yeah.
How does that sound?
I think that's great. And then just to connect this to like the one sentence summary that we had earlier, how are you sharing information? Where are you storing your information? In a quantum computer, you store it in a thing called a qubit. And so that's the last word in DiVincenzo's criteria number 1. So now let's talk about it. One thing we mentioned last time, and you kind of already hinted at it, but I want to make this explicit. There are lots of different kinds of quantum computers, and there's different kinds because people are using different physical things for qubits. So we just want to focus on one kind of qubit that some companies are using, which is a trapped ion, which you just mentioned. But just, to be explicitly clear, we could have chosen to talk about other qubits like superconducting qubits, which maybe you'll mention, and then there's other kinds. But just for this podcast, we're going to pick one and kind of talk about that a little bit.
That sounds great.
Yeah. Okay, so Adam, what is, so the qubit we want to talk about is a trapped ion. Okay, so that's an adjective and a noun. So let's talk about the noun first. Can you please remind us what an ion is?
Yeah, an ion is just an atom that has some charge on it. And the word ion actually goes back quite a ways. I think Faraday first talked about ions in the 1830s, and that was in the context of electrolysis, of like electricity kind of moving through water from one part of like an anode to a cathode. So kind of like basically how you can stick a battery into water kind of and make hydrogen and oxygen. There was some kind of movement, and the word ion comes from the Greek to move. And it wasn't until much later, so it wasn't until a fair amount later that there was more work done on what an ion actually is, instead of just describing that it's some kind of thing that's moving charge through the water. That's what Faraday said. It took a little while to figure out more concretely what that was, and that ended up earning a couple of Nobel Prizes around ions much later in the early 1900s. So that's kind of like our history of discovery and characterization of ions. We've known about these things for a long time.
One thing that could be helpful for folks to know is that some elements or some atoms are better to work with for quantum computers than others. So I was reading about this recently, and apparently elements from groups 2A and 2B of the periodic table are kind of the preferred ones. So that includes beryllium, magnesium, calcium, ytterbium, zinc, and others. And I think that I don't want to jump too quickly to the rest of criteria number 1, but part of that is going into the well-characterized part of well-characterized qubit, because in order to really manipulate these things, actually, let me say it like this. All of those elements that I just listed, you find them in nature, right? Like no one is like baking ytterbium in their oven or something. Like it's just it's just out there in the world. But the thing is, these are atoms. So you have to think about, how do I want to turn this atom into a qubit? It's not just naturally a qubit. I mean, it naturally has the potential to be one, but you have to construct a device that's going to knock off an electron to ionize it, to give it a positive charge. And then you, as the engineer or the physicist, have to decide like which of the many energy levels that you can choose from will be your ground state, and which will be your excited state. So usually you have 2 energy levels, and these 2 options are representing the qubit, right? A qubit is like a system with 2 options that are analogous to like heads or tails, or light on or light off. So in physics, quantum physics, your 2 options are going to be, hey, my electron is in this energy level or in this energy level. But you have lots of choices in each of these elements. And so I think the reason for choosing these particular elements off the periodic table is that they have certain properties, or they're folks know how to manipulate them with very specific lasers, with very specific wavelengths for certain time durations. And you have to know all of that nitty-gritty stuff. So, I mean, I guess I jumped the gun a little bit, but that's kind of getting into what the well-characterized means. And you just don't go and pick up any atom or any ion off the street. Like, there's specific ones because, well, they have properties that you can then harness later on to do your fancy stuff.
Yeah, no, I think that's, that's right. So I think that one of the big points here is that these things have been known about for a long time. Ions and even how to manipulate ions generally have been known about for a long time. And now we have new technology and new knowledge to help sort of harness those fundamental pieces into something that can be a quantum computer.
So, okay, we talked about ions for a little bit, but there's this adjective, right? Trapped ions, trapped ion quantum computing. So maybe we should talk about the trap now. Any thoughts on that?
Yeah, that sounds great. Yeah, I mean, I can start, but I definitely want to hear your thoughts on this. But one of the benefits of an ion is that it has a charge, and that charge means that that the whole ion, that whole atomic unit, can be manipulated in motion using an electric field.
Yeah.
So if you have something that's charged, you can use an electric field to control where it is.
Yeah.
And so that's really the important piece here with the ion part. And you can do this with neutral atoms too. People may have heard of neutral atom quantum computers. You just have to do that a little bit differently in a different way because your atom is neutral instead of an ion. But if you have an ion, you can use electric fields to control where it is. And from my understanding, the way that that's normally done, what you want in a trapped ion computer, a quantum computer, is you want to have a sequence or a chain of trapped ions on your chip that's in that's the computing part of your quantum computer. And to do that, you can kind of create these wells of electric fields to control and to trap your ion. And the way that I think about this, and then I want to hear what you think, Tai-Danae, is, without getting into just too much detail, electric fields are kind of shaped more like a saddle. Like an atom might be stabilized. Let's see if I can make it like this, like stabilized in one direction, but it can fall off in the other direction. So you're really, with a single electric field, you're really only able to control where it is on this one axis. But what you can do is you can, some really fancy control equipment, you can oscillate this electric field so that you're moving back and forth like this, and then you're trapping the ion on both dimensions. So it wants to start to roll off, but you switch the field and it keeps it in place, but then it starts to roll off the other way and you switch the field again, and you're kind of like doing like this, or like a Pringle, a Pringle chip, exactly. like spinning around in a plane. So that's the kind of the trapped piece, and you're able to have that control because that ion, whether it's calcium or something else, has a charge to it. So you can manipulate its motion with an electric field. What do you think about that, Tai-Danae?
No,
I'm sure
no, that's good
to add.
Well, no, I think that's good. The only thing I would say is that, like, you may ask, why do that? So maybe we could back up a little bit. Ideally, a trap is like, I think you used the word well. So it's like a little bowl, right? So ideally, if you have a bowl, you'd like your ion to just sit in there. But listen, ions are so small, they do not feel gravitational effects, right? So you can't just actually get a bowl and stick an ion in because gravity's not going to pull it down. So instead, your bowl is really made out, the bowl that you'd want, it's really made out of an electric field. But it turns out, for technical, mathematical and physical reasons, which I do not fully understand, but I think it's a theorem, you cannot have an electric field that's just like a stationary bowl like that. Okay, which is why you have to have this Pringle type thing, which you can then spin. Like anyone can imagine, take a Pringle like this and then spin it really quick. Now you've basically got a bowl. Okay, so that's kind of the trap, but the reason you have to take this Pringle type detour is because actually the math says that this is not possible. But here's the thing, okay? There's one more step to this, which I think is really interesting. You've got this necklace of ions. What you actually want to do is to also make sure that they, let me say it like this. atoms have energy associated to them, right? So they're kind of moving around, and you don't want them to move around so much, because what if they jump out of the well, right? Or like these things are like, they're just wiggly. So another step to this is something called cooling. So I'm using quotes like this because what I mean is that you want to kind of remove some of that kinetic energy. If you can slow your movement down, that's kind of analogous to cooling them. So then there's other technical things where it involves shooting more lasers at them to kind of keep them still so they don't jump out of the well like that. Mm-hmm. But in addition to all of that, okay, imagine, Adam, you've got a bunch of positively charged teeny tiny particles. What do we know about things that have the same charge?
They don't like to be next to each other.
Sure, they don't like to be next to each other. Right? So there's like some repelling force between them, which is called Coulomb force, but they can't, escape too much because they're in this well. So you can imagine, like here, I'm an ion, and like there's one over there, and I'm getting close to it, but then I feel that electric force called Coulomb force, and then I'm bouncing back over here. Oh, but no, I got too close to this one over here, so then I'm bouncing back. So you can imagine how all of these ions are kind of jiggling a little bit. And that turns out to be extremely important. So that is not a bad thing. But later, I think in another episode, we'll actually see that in addition to these energy levels that individual ions can have, this ability to trap them with lasers while also being aware of the Coulomb force or the kind of repelling that they're feeling against each other gives a total motion to the whole chain. And that understanding that total motion together with individual energy levels of the individual ions, that is like a whole package deal that comes into the nitty-gritty specifics of how to run this computer.
Yeah, no, it's things get complicated pretty quickly. But yeah, I'm looking forward to hopefully being able to jump into that. I have one other question that comes to the top of my mind when we're talking about we're going through a lot to try to get this like necklace or this chain of ions like sitting there on the chip. And so I think a reasonable question is like, why do we need to keep them in a single spot? Like, why can't we just have like instead of a bowl of one, why can't we just have a pool of a whole bunch of ions or atoms sitting in there? And my understanding for that also hits under the well-characterized piece, but please jump in there, Tai-Danae.
No, wait, tell us.
You need to manipulate. Oh, okay. Okay, I'll try. That we need to manipulate those atoms. So like you mentioned before about changing energy levels, we're zapping these with lasers and changing the energy level. And that's basically going from the ground state to the excited state and then eventually back to the ground state. And it's those two different states that allow us to do computation. And if we want to be able to control that well, we have to know which ion we're dealing with. And we have to know that if we take aim and shoot a laser at a place, we need to know where to shoot it. And we need to know who got shot and what its energy level is getting moved to, and like keep track of all that. So I think that at the most fundamental level, the reason why, the engineers, I was about to say we, but engineers and scientists that are not me, them, why they need to do that, go through all that trouble of the spinning Pringle and all the lasers and all that kind of stuff to get these in a nice line isn't just because like it looks nice, but it's actually a fundamental piece of this type of infrastructure of a quantum computer that you need to know where the qubits are, and you need to know what state they're in. And in order to do that, you have to keep track of where they are. And the best way to do that is to keep them in a single spot, or at least as close as possible to a single spot where you know how to like maintain that accounting. At least that's my understanding of it.
No, I think that's correct. Although let me say two things that are a little above my pay grade, but I'm going to say them anyway. Did you know, so there are at least two companies that are dealing with this kind of technology. One is Honeywell, which I think is now called Continuum, and then there's also IonQ. So Honeywell, one of their quantum computers actually has like a racetrack design. So instead of just a line, it kind of looks like an oval. But then also, there's, I think also at Honeywell, I was listening to a talk actually at CUNY, City University of New York last year. And I think now they have the ability, okay, imagine this. You've got a whole bunch of really teeny tiny ions in a line, right? And you want to like shoot ion number 7 with a laser. But because they're so close, there's the potential for kind of leakage or noise to affect the other neighboring ions that you don't want. So I think there's now this idea where you can actually remove ion number 7 and ion number 9. Let's say you want to entangle them, and you kind of separate them over here, and then you do your magic to them, and then you can bring them back. So I think these are like things that people are thinking about how best to manipulate these qubits while also minimizing errors that you don't want. Yeah. So I think a line is a place to start, but I think that they're also maybe expanding that idea a little bit.
No, definitely. And that's if I remember correctly, that's a quantum charged coupled device. I don't think it's coupled charge. I think it's charge coupled QCCDs.
Oh,
so,
right.
And I think that's a really good transition into the last part that we want to talk about, which is really the first part of DiVincenzo's first criteria, which is scale. Because what you're describing, I think, is an attempted solution to the problem of scaling. And you kind of got into this a little bit before around that motion in the chain of qubits, which is like beneficial, and we'll talk about that, but up to a point. If everything starts moving in a way that's a little bit less controllable, and that motion changes as you add more and more ions to that chain, you start to run up against a hard limit. And then there's another scaling issue of having all of these, all of these different qubits need different control devices, so different lasers that can shine on all of them. And as you pack things closer together, or you have more and more ions, that can actually change the sensitivity of each of those ions to a laser that you're using to control it. So your control of the wavelength of that laser has to get better and better as you have more and more ions. So there's that scaling problem, and those are hard, very difficult problems that haven't been fully solved yet. And so this QCCD idea of this racetrack that you're talking about is, I think, one of the ways that engineers are looking to be able to try to pack more qubits into the system, but to be able to move them around in certain ways so that you reduce that reliance on super finely tuned lasers, and also can control that motion of the entire chain that you were talking about before. So that's my understanding of how all that kind of fits together into DiVincenzo's criteria.
Yeah, exactly. So, do ion-trapped quantum computers satisfy DiVincenzo's criteria number 1? Like, yes, because they're qubits and they're physical and they're well-characterized, but can we scale them? I mean, that's what people are working on. I think no quantum computer satisfies all of these criteria because everyone is working on scaling right now. But just to give people an idea of the number, I think, by way of reference, IBM's biggest quantum computer now, which is not trapped ion, that's superconducting, has 433 qubits. Okay, by way of reference, if I looked this up correctly, I think IonQ's current quantum computer has 32. Okay, which is still a small number. So just, if people are wondering how many of these things are there, 32. It's not a super big number, but it's a lot bigger than they've had before. So this is good.
Yeah, definitely. And let's show a picture. So I know we talked about this before. So I'll actually have a picture here that we can share that is an IonQ chip. And what you're seeing here is a composite image. So this is the actual quantum computer chip there. And you see all those blue, or maybe they're purple, I'm kind of colorblind, but all those dots. And those are the trapped ions. And that's the composite piece of the image. Zoomed in on that little slot in the middle of the chip. What's in there are all those ions. They're blown out in this picture. And you'll notice there's more than the 32 or so that you mentioned. But this is more of like a research chip. So this is not commercially available at the moment. But this scaling issue is the big issue that folks are working on, or one of the big issues that folks are working on when it comes to trapped ions. So, I would say that out of all of the pieces of the criterion one for DiVincenzo's, scaling is the toughest part right now with trapped ions. When we're talking about a physical system, we just mean something that's real, not just theory. So we've got that. And the well-characterized piece, we know about ions, we know how to manipulate their energy levels, that's all good, which is great. And there's some other benefits of trapped ions, but really the scale issue. And this is shared by some other types of quantum computers, but trapped ion, that's as far as I understand, that's the big thing that folks are really trying to work on.
Yeah. Okay. This is good. So just to wrap this up, I would like us to take a moment and appreciate how great this is, okay? As you know, I have a background in mathematics. The first time I heard qubit, the answer I'm given is a qubit is a unit vector in a two-dimensional Hilbert space. Or, if a more maybe pedestrian explanation is it's like, a column of two numbers so that if you square them, you get one. Or maybe they're not real numbers or something. Okay, whatever. But I love that we were able to, at least in our minds, grasp some calcium ions or some ytterbium ions and like knock off an electron and then, kind of think about the different energy levels. And by the way, we totally skimmed over a lot of details there. There are things called like optical qubits or hyperfine qubits, and this has to do with exactly which energy levels you're working with. But the fact that all of that stuff can be understood and manipulated, and we'll get into that later when we go to the other criteria, but in a very physical, tangible sense, at least for me personally, really helped put some meat on the more theoretical ideas, which I think usually it's like the theory that we read about in pop sci, understandably, because the engineering is very technical and not as accessible. But I hope, in the past few minutes, we were able to at least make some of this bite-sized. I don't know. I thought this was super fun.
Me too. And I mean, you and me are the only ones talking here. So as long as we think about, well, nice. I think we're good, right?
Exactly.
So yeah, and we'll get into some more of those details. But also, we'll pop something into the description. There's a really great article that we've used, and that I know other folks have used. I think it's from a Penny Lane article.
Oh, so good.
That talks about trapped ions in general, and trapped ion quantum computers. So we'll drop that in there for folks that want to get into like the optical / hyperfine, and we'll talk about all that manipulation and stuff moving forward. I'm going to try to spend like 30 seconds on the superconducting piece really quick with DiVincenzo's, and kind of, compare that to what's going on with trapped ion. So the, well-characterized physical system, in superconducting quantum computers, the physical system, it's physical, like it's not just a theory, but the well-characterized part is a circuit that engineers have made to mimic these energy levels of atoms. So we talked a little bit before about energy level of atoms and how they can be used as a qubit. So that's what's happening in a superconducting quantum computer. But it's mocking that up in a circuit that can be printed like in lithography style on a semiconductor, like on a computer chip, essentially. It has to be kept really cold. So that there's some scaling issues there. There's scaling issues both in the fact that those qubits, each one of those like little chips, you can think of the piece of the chip. I don't want to get too technical, but these Josephine junctions for people that that know a little bit more about these. But each of those is a qubit. Those can be packed onto chips in a similar way that you can put transistors on regular CPUs, GPUs, things like that. But there's scaling issues there because things have to be kept really, really cold in order for the superconductivity to work. And the control that you need to manipulate those circuits requires a lot of infrastructure. Right. So the number of just the wires that have to be like plugged in and tuned in, and everything needs to be just right in order for that to work. It's really a big challenge. But as you mentioned before, folks are doing this, and there's a 433 qubits superconducting quantum computer, and we're in the double digits for things like trapped ions. So the scalability issue could be a little bit easier there at some point in the scaling process, but there's other advantages and disadvantages of these different types of quantum computers, or these different types of qubits. And we were just talking about 2. There are like another 7 or 10 at least types of qubits. So just to let you know a little bit about what's happening between trapped ions and superconducting, that's the short version.
No, that's perfect. Yeah. And I think even people can like in their mind separate between artificial qubits, which is like superconducting. Artificial, those are the ones that are trying to mimic what's naturally available in natural qubits, which are like ions. So, all right.
Yeah, and some folks even call those artificial atoms.
Yeah,
like the superconducting qubits. Yeah.
Exactly.
So yeah, let's talk a little bit about next time.
Yeah. So next time we are just going to move right down our list of DiVincenzo's criteria. Let's not say what number 2 is, formally if we were to look up in his 2000 paper, but can you just give us the Cliff Notes friendly version? What is the next criteria we'll be talking about?
Sure. Yeah, I'll try to do that. Basically, it's about qubit initialization and manipulation. So initialization just meaning like getting them kind of all in the same state that we know so that we can then manipulate them. So that's basically what the second criteria is about, is being able to get them reliably into their ground state. So getting everybody looking the same, and then being able to reliably control those qubits in a way that is predictable and understandable to us. And I think that a piece of that is some error is acceptable there, but it needs to be a small enough amount of error in that control that we can account for that. And I think that's an important part of that criteria.
Excellent. Okay, I'm looking forward to this discussion, and we hope to see everyone next time.